please go over the structure of the phospholipid bilayer that we illustrated in class. Know the major components in that bilayer, and know a description of their function. What role are they playing in the bilayer? Especially the phospholipids themselves, and especially their amphipathic nature. That's extremely important to get an understanding of, because that will help you understand why some things can get through the membrane because they're nonpolar, and why other things cannot because they are polar. Okay, let's also begin to think about transport across the membrane and some of the driving forces that want to move particles through that membrane as well. So let's think about our driving forces. So we want to think about some terms that we used here. So be comfortable describing these terms because you will see them and you should have an understanding of what they mean. So VM is the membrane potential. All right. And we can describe that as the uneven distribution of charge across the membrane. And we kind of describe this, right? Because we have a cell membrane and because it is selectively permeable, it's going to allow some things in and some things out. Also, because of some of the channels and pumps that we have present on the membrane, it's going to create two separate intracellular and extracellular environments such that we have a separation of charge. We have, this is the ECF, this is the ICF. We have more positive charge out here, and we have more negative charge in here. So that separation of charge is what creates the membrane potential. And this is usually a value of around negative 70 millivolts, which means that inside the cell, so it's referencing the inside of the cell, is negative 70 with respect to the outside of the cell. And the value on this 70 is the magnitude or the strength, right? The proportion of that difference, that separation. Another term we want to understand well is the equilibrium potential. And this is described as, first of all, it's determined by the concentration gradient. Okay. It is also going to be specific for individual ions. Okay. We so far have mentioned the specific value for potassium. So for potassium, potassium's equilibrium potential is going to be negative 94. The equilibrium potential for potassium equals negative 94 millivolts, which means that when the cell is at a membrane potential of negative 94, potassium is at equilibrium. It's no longer moving. Its electrical force is equal and opposite to its chemical force. And at this specific membrane potential, it is said to be at equilibrium. Okay, so that's what our equilibrium potential means. There's no movement for the ion because its forces are canceling out. Okay, so no net movement as the ECF, or the EDF, excuse me, the electrical driving force is equal and opposite to the chemical driving force. Okay, very important concept about the equilibrium potential. Let's think about the CDF and EDF. So just to describe the factors that determine those. So the CDF is determined by the concentration gradient. Okay, and this wants to move particles from high to low concentration. So moves particles from high to low concentration. We can also think about the EDF, which is slightly more complex. This is determined by the charge on the particle and the polarity of the cell. Okay. So when you think about the EDF, the electrical driving force, it's really going to be for charged particles. So we want to think about ions here, right? Ionic movement. And it's going to be in opposite directions, ionic movement in opposite direction. This is why the polarity of the cell matters and the charge on the particle matters, because positive charged particles will want to move into a negative area of the cell. Negatively charged particles will want to move in a positive area of the cell. So ionic movement toward the opposite environment. Okay. All right. Now we can combine those two forces and think about our ECDF, our electrochemical driving force, which is really the sum of both forces. Okay. And in our algorithm that we drew, definitely go over that algorithm as well. We said that when the forces are in the same direction, so if forces are in the same direction, then we simply sum them. However, if forces are in opposite direction, if forces are in opposite direction, then we're going to think about looking at the equilibrium potential and comparing that then we compare equilibrium potential versus the membrane potential, and we determine which force is stronger, okay? So we're basically comparing the equilibrium potential to the membrane potential, and then the algorithm will sort of take over and determine what force is going to be the overall direction. Okay, so these are our driving forces. Again, go over this, go over the algorithm, okay? And definitely know what direction of movement we're going to see for each. Okay, we're running down on time, so let's quickly go to our last packet, which is the membrane transport. All right, this is probably the most recent, so I imagine this may be a topic that you're be a little bit more strong in or have less difficulty with. So let's go over membrane transport. So we talked about, and for this, it's really about classifying these really well, right? The questions will ask you to have a good understanding of how can you differentiate active transport from passive, spontaneous movement from, or spontaneous or downhill from uphill movement? How can you differentiate movement through channels versus facilitated movement versus simple diffusion? So there's a table that we looked at the end of that slides on this, as well as what we're going to review here, but have a good understanding of differentiating these various mechanisms of transport. So we can think about two general categories. Another color. Two general categories of transport. We have active transport or let's do passive on the side. So passive transport. And just to describe passive transport here, we said that this was spontaneous, downhill, and it is going to donate energy. This is extremely important to understand as it applies to secondary active transport. We need to remember that when things move down their concentration gradient, they give up or liberate energy. So it's going to donate energy. Okay. And we can compare that to active transport, which is non-spontaneous. It's going to be uphill, so it's going to take some energy. Okay, it's going to require energy input. Let's look at these subtypes and the examples. So under passive transport, we can think about 3 examples here. So we have simple diffusion. And simple diffusion, first off, is based on the concentration gradient. Okay. It's also going to be determined by the magnitude of the driving force. Right? The bigger the strength of the driving force or the concentration gradient, the bigger or the faster the rate of simple diffusion. So it's, the rate is going to be determined by the magnitude of the driving force, the surface area available for exchange, and the membrane permeability. Oops, running out of space here. There we go. Membrane permeability. So these are the 3 factors that determine the rate. I'm going to just put that in here. So the rate is determined by these 3 factors. Now, under the membrane permeability, we can think about some other sub-factors, right, that would help to determine the membrane permeability. So we want to think about the lipid solubility. We want to think about the size and charge of the molecule or particle. Size, charge, and shape, right? If it's really bulky and big and clunky, it's not going to go through the membrane. We're going to have decreased permeability. And then we want to think about the temperature, right? The temperature. Okay. Another one to think about is the thickness of the membrane. I apologize that got really small down here, but hopefully you can see. So the lipid solubility, the size, charge, and shape, and the temperature, as well as the thickness. So things that are lipid soluble or non-polar will get through easily. Things that are small, non-charged, right, will get through easily. Things that are the thinner membrane, the thinner the membrane will also increase the permeability. Let's shift gears. Let's move on to a second example of passive transport. So again, still moving down the concentration gradient. This time we need some help. So first is the facilitated diffusion. And I know we're running out of time, so I'm going to try to move really quickly here. So facilitated diffusion versus channels. All right. Facilitated diffusion is going to be a transmembrane protein. right? And this would be an example of a carrier. The example we talked about was the GLUT4 transporter, okay? So this is going to actively help the particle get through. Channels are also transmembrane. However, these are going to act as passages or passageways or pores, okay? Examples of this would be ion channels, right? And we talk about many different subtypes. And these are going to be passively involved in getting the molecule through. Let's move on and think about two primary types of active transport. So there's primary and secondary active transport, okay? And the major examples was that primary is going to be reliant on hydrolysis of ATP. So we have to hydrolyze ATP in order for the primary transport. So it's going to be the enzyme that's required is going to be coupled to a phosphate being donated, and that's going to liberate the energy required for active transport. Example here is the sodium-potassium pump. So the sodium-potassium pump, and that can be compared to secondary active transport, where the energy required is going to be released from another molecule moving passively. So the energy required is released from another molecule moving passively, right? Or down the concentration gradient. The example that we talked about was the sodium-linked glucose transporter. Okay, and this was specifically an example of counter transport. I'm sorry, this was co-transport, right? This was co-transport. Co-transport, okay? But do go over the other examples that we talked about, which would have been counter transport, such as the proton linked pump as well.